Anyway, I will repeat. So don't worry about this one. I will repeat as a quick for this because I forget recording. Sorry. So again, excuse me, give me 3 or 4 minutes to repeat this item. Transistor as meaning. I forget recording, so I will repeat. Sorry, excuse me for that. Transistor as meaning is a device, semi-electron device, has 3 areas, P, N, and P, or N, P, and N. This is first. In each one, I will focus on this one. See the width of base. It's 1/150 comparing with collector and emitter. I'm repeating for recordings, excuse me. So here, see, we have emitter, that means emits, sending hole or electrons. Collector collects them. And we have very small area called base. This base is, we'll talk about this base now. Okay, transistor not a new device. It's from 1956, so it's old, almost 80 years ago. They will make this transistor. We can express transistor as 2 diodes. See, P, N, and this is P. So it's P, N, P, or opposite, we can say it is N, P, N. So we have 2 models of a transistor, PNP or NPN. See, also we have here 2 powers. We'll talk about power. Transistor has a name, Pupillar, Junction, Transistor. Okay, Pupillar, that means 2. What are these junction? Now let's see. This junction is this junction, this area. This area. Here is junction, and this is the second junction. So this is called emitter, junction. This is called collector, junction. We talk about junction, if you remember, in diode. So if I want to draw, this is emitter, junction, this is collector, junction, emitter, junction, collector, junction. So this is the first thing, pupillar, junction, that means 2. Junction, transistor. Okay, myself, we are repeating because I forget the code. If we start here with this model, if just I connect one battery, this one, and I leave this open, what will happen? Here E, so we have majority, now it's good for your repeating, minority. For whole is majority is whole, for this is electrons. Minority here, electrons, whole. So we have majority current will go from here, then come. See this area? Where is this area? Is very small, the pressure region. So majority of current will go from emitter and return back here. Also we have hole, but very small. So also continue here, conventional current. So this is called majority current or carriers. Also we have small currents for those, and this from here to here, but it's very small, so we can ignore it. This is also minority currents, as you know, but it's very small, so we can ignore it comparing with majority currents. Now, another case is this. We have, or we connected battery, VCC. Okay. By the way, see this junction. It is, you can say positive with anode, negative with cathode. So it is forward bias. See here, positive with negative with positive. So it is reverse.
Напиши на почту учителю.
Close your mic.
Лектор написал, он ответил.
Okay, so this is reverse bias. So in transistor, this is a new idea. We have forward, we have reverse. This is forward bias. This is reverse bias. So also we have dual bias. First one is forward, another one is reverse. Forward bias, reverse bias. Okay, we have 10 minutes, then we will close. After that, take a break for 11, okay? So we have forward bias and reverse bias. We have forward bias and reverse bias. Just a minute, excuse me. Let's see this one. What about current here? For this one, this is positive with negative. Sorry, it's in. And here we have negative with positive. So as you know, in reverse bias, we have minority current. Because here we have, this is in N, we have majority, minority. Majority here is electrons, hole, and here again, hole, electrons. But we are working here under reverse bias. So this is reverse bias, that's mean minority. So we have a current, see, electrons and hole. Go from here, hole positive, come here, go to the battery, return back here. Same thing for electrons, but as a conventional current, see this one. So we are, what about majority? There is no majority because we are working in reverse bias. Remember diode, this is diode, this is forward, and this is for reverse. So this forward is here, and reverse, we are working here for this one. This is the reverse. So we don't have majority, we have just minority current. So now totally, if just to connect VEE, we have majority carriers or majority current because we are working under forward bias. We studied this in diode. Again, if we are working in just VCC or reverse bias, just we have minority carriers or minority current. We don't have majority current. Is it clear for you? Any question about this? Now, if we connect VEE and VCC, what will happen? If we connect VEE and VCC, what will happen? It's another question. Now, let's see what will happen if we are connected two power, VEE and VCC together. See here? Okay, this is very important. See here, here we have majority carriers. See this arrow? Current start from B, arrive to here. Here we have very narrow depletion region because this is forward. And here we have big depletion region because it is reverse R. Okay, what about current? See current here, start from emitter, arrive to this area. In this area, we have very small recombination. So we'll continue to the collector. And very small amount return to the button. This is for, what is the name for this one? It is majority carrier, majority current. So for majority current, start from emitter. Emitter is my hand, emits. Carrier, P or E, based on NBN or PNB. Because we have here a very small area, and this again, second thing, this area is very narrow. So a little bit will return back to the B, and majority will continue to the collector. Repeat. Emitter emits, send. Carrier, majority carrier. They will arrive, carrier to this area. But because this area, the depletion is very small, majority will continue. And because also B is small, majority still continue to the collector. And we have very small current for majority carrier will return back to B and to button. This is for majority. For minority, we have also current. This one is current. We have also current, excuse me. Small current. This is called minority current. Minority current. So we have now two currents, not one. Pupillar, it's two. We have majority current start from emitter, arrive to the depletion region, but because the depletion region is very small, so we can skip it. And we will arrive to B because B also is very small, we can skip it and continue to collector. And we have minority current based on reverse bias. This is reverse bias, see? This is reverse bias. Positive with negative, negative with positive. So we have minority current on collector. So you can see on collector we have, this one, okay. We have two currents. We have majority and we have minority. Any question about this? Any question about this? It's clear for you? Now, totally. We have IE, IB, IC. Emitter emits, B, small current, and majority of you arrive to collector. This is for majority, forward bias. For reverse bias, we have small current between P and E because we are working under reverse bias. So on collector, we have two currents, pupillar. Every time pupillar, we have two currents. Collector, majority and minority in collector. Okay, any question about this? Any question? Green one is minority, my friend Ahmed. Ahmed is minority. Okay, it's minority current. This one. Okay, repeat again. This is minority. Okay, take a break until 11, then we return back. Okay, any question? Dark green. Same thing. Same thing. Just I change the bin. Okay, a break until 11, then we'll return back. Any question? Okay, take care for yourself. 11 will return back. I will keep this one recording. Okay, and then I will start again at 11. Have a nice day. Take care for yourself. Bye-bye. Okay, repeat again. Forget recording because I forget online. Okay, doesn't matter. It's good for you. Repeat. Okay, no problem. No problem for that. We start. Forget recording. Because we didn't use online. Okay. Again, my friend, repeat. Because I forget recording. Thank you. Which one? What's your name? I forget your name. 1 second. So again, This is, repeat, this is, it's a majority current, C. And we have small current, IB. And we have minority current here, also IC. So we can consider a transistor as, based on Kirchhoff law number 1, as node. So this is IE. This is IB. And this is IC. This is our 24P NP. Okay, let's continue about this one and study transistor from as a symbol. This is the symbol of a transistor. See again, repeat, we have two power, or we have two powers. This is positive with positive, negative with negative. So it's forward. Yes. Now we have negative, positive, but here we have positive, negative. So this one is, see, reverse. So we have in transistor two powers, forward bias and reverse bias. Third thing about symbol, this transistor symbol. See this one, this is the symbol for transistor. Keep this one before, and this, and this. Okay, I will write again, head of arrow in, see, EP indicates to in. For example, here in this one, this is E and this is P. This is arrow. Where is N? N is here. P, N. So this one. Head of arrow indicates to N. So this is N. Now let's go to another one, opposite one in our book. It is NPN. Let's see first all the direction of arrows. This is IB, IE, and IC. Why is this? B in, this is direction. Usually from positive to negative. From positive to negative. We are dealing with conventional current. And in conventional current will go from positive to negative. For that reason, see my friend, direction of current is out. Out, out. With that, IC positive, IB equal IE, still correct. Why? Because I need conventional current from positive to negative. Here, why we flip arrow here? And let's see the voltage here. It is negative, positive, negative, negative with negative, forward. Positive with positive is forward. Good. Second one, positive with negative, it is reverse. Negative with positive, it is reverse. So it's here, it's reverse. Here it is forward. Now, symbol of transistor NPN. Again, this is my transistor. Now, NPN. This is my goal. EB. Direction from direction to N. NEB. This is EP. So arrow or head of arrow indicates to the N. So see this one. This is N, P, N. So if you see the symbol, you have to know if this is what is P, N, P, or N, P, N, and you have to know also direction of current. It is in or out. Anything about this one? Any question about this one? Okay. Now let's see last formula here is this one. IC, it is IC majority, positive ICO minority. If you return back up in our book, see this here, how many currents do we have? Expand. See here, in collector, we are talking about collector here. We have first current, this one, I, E, oh sorry, I will use later, explain later this one. It is I, C, majority, and we have a small current, this one called I, C, O, minority. Why is O this one? Because this is based on minority carriers. Or if you remember, we took like this one in diode, it was I saturation. Sorry, I saturation. Or I O. Sometimes that we use this one. Or IS, we use this one, IS. If you remember the formula of diode, ID equal IS, blah, 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 blah. So this is IS, minority carriers. So in collector, we have two currents, one for majority and one for minority. IC equal IC majority plus ICO minority. Any question about this? This current called leakage, if you know, it's the code leakage current. Now, I'm going to use ICO symbol, IC current with emitter or emitter terminal open. So ICO or IS, simply. But here I'm going to use ICO or IC minority. Any question about this? Those two formula, 3.1, 3.2 is memorization. You have to know and study because you have to use this data. Now, in diode, okay, here I'm going to use this white area. Just can't find. No. In diode, we have three connections. What are those? Actually, in transistor. First, second one, third one. If you see the transistor, this transistor, P, N, V, for example, and this is the arrow. Emitter, base, collector. So, usually, we will connect E or P or C to the ground. If I connect B to the ground, so it has a name, common base. If I connect emitter to the ground, has a name, common emitter. If I connect collector to the ground, has a name, common collector. So usually we have to connect either E or B or C to the ground because we have two power, so we need one as a ground. So for that reason, for common base, we have CP symbol. For common emitter, we have CE symbol. For common conductor, we have CC symbol. So we have common base, model, or configuration, transistors, configuration, junctions. We have common base, we have common emitter, and we have common collector. Usually, if you want to study transistor for study, it's the main one. Main model, if you want to study transistor, is common base to understand the concept of transistor. But in our life, we are using this practical model. And common model. Common collector is a little bit used. So we'll focus about common base and common emitter. Because common collector is a little bit used, we can use just common base and common emitter. So if you want to study transistor as a transistor, you have to study starting from common base. And if you want to use transistor in your life, you gotta start from common emitter. So for that reason, see our book. We started from common base configuration. Common base configuration, that's mean we have, I will draw here, for example, see, I have transistor, for example, P in P, and this is head of arrow here. Then see my hand. This is for ground, common base. Then I will connect it to the positive, negative. See, this is positive, negative. V, E, E, V, C, C, and this is the common point. Clear for you how we can connect? So this is common base. See, in common base, we have two areas. We can express transistor. I can accept, but not exactly correct, as a two diode. See, this is the first diode. PN is a diode. And we have another diode. This one is another diode. So this is D1, D2. So we can draw this one as here. Okay. This diode first to a diode, forward diode, and another diode is reverse diode. This is here. Base, emitter, collector. So if you want to study transistor, excuse me, try to use this model, two diodes. As I told you, it's not exactly correct, but it's helping model. See, this is in, this is out. Input circuit, this is current in, this is out. I, E, I, C, and this is I. So we have input current or input diode, output diode. We can. For that reason, in transistor, we have also, okay, this one, we have input and we have out. So we have input circuit or input characteristic for this one, and here we have output characteristic. Transistor means transfer impedance. Repeat. Transistor, transfer resistance or impedance. Resistance, use the resistance. Transfer resistance. That's mean I have here ZI, inshallah this is for 2, and here we have ZO. So I will change from ZI to another ZO. How can I change this one using the transfer resistance? Transistor. This gives to me transistor. Transfer resistance. So I have ZI for input, ZO for output, but ZI not like ZO. Who did this one? Transistor did. So for that reason, transistor came from transfer resistance, change resistance. And we have input character in this circle or in this area. In this area, we have input and we have output in this area. Between input and output, there is a relationship we shall study today. Why is this? Any question about this? First of all, clear for you? Is it clear for you? Any question about this? Okay. So let's see this one. It's here is like a diode. It is like a diode. Exactly correct. So if you see this one, this model, it is, I will draw again transistor. This is transistor, emitter, base collector, P, N, P, this is arrow. So let's now draw the battery. Common base, VEE, VCC, IP, IE, sorry, IE, correct, IE, IP, IC. This is, you have volt, V, VE, V, CE. Sorry, we have VCB. Sorry, I made a mistake. VCB. And here we have another volt, VCE. I will draw for you, it's important. Okay, keep this later. I will explain this about voltage. Now, why is this? This is the input character. It is IE with VBE. Okay, Hujam, why we flip? If you flip, you just change the sign. So for that reason, we are using VBE. You can use VEB, yes, absolutely correct, but you have to change the sign. When, see my friend, VCB is constant. What is this, Hujam? Usually, if you have two batteries like this, I'm studying this one, input character. So you must make this one is constant. If you remember, for example, in physics, d over dx positive, d over dy, partial differential. So same like this, Here I have VEE and VCC. So for that reason, I will keep this one constant. See this VCB? VCB is constant. And just to change IE with VEBE when VCB is constant. Again, input character is IE, input current. Input current with input voltage when output voltage is constant. So first of all, you have to adjust output voltage, then draw this one. Now let's see the input current. See my friend, input current, if we draw the equivalent, this one, if you remember this, E, P, C. So this is, it's diode. Usually it's silicon. We are using a transistor silicon. So for silicon, we need 0706 to open. So see this area, it's off. No current. Add 0607, my current start to increase. Based on VCB, for example, for VCB1 or VCB10 over VCB2. So input characteristics for silicon, it's like input for diode. From 0 to VT, 0607 at silicon, there is no current. After that, current will increase rapidly. So if I want to draw input characteristics for diode, first of all, make output voltage as a constant, CV1 or 10 or 20. After that, change IE with VBE. You can see if I increase VBE until 0607, there is no current. Then add VT for diode, like this one, my current will increase. Any question about this one? Any question about this one? So input characteristic for silicon, for transistor-like input characteristic for diode, when the output voltage is constant. Any question? Yes or no? Okay. Now continue. Output characteristic. It's up here. Excuse me. Yes. Okay. We have 10 minutes. Okay. Then we start third hour. See this is the characteristic here. We have another thing. Here we have, okay, first of all, see the axis. IC, so it's output current with VCB output voltage. When C input, this is input current is constant. So now we can talk about two characteristics: input characteristic and output. Input, it is IE equal as a function of VBE when the VCB is constant. For input. For output is see this one, IC as a function of VCB when the input current, not input current, is constant. Focus about this, excuse me. Here volt, here current. So input characteristic is input current as a function of input voltage when the output voltage is constant. It's input. Output is output current as a function of output voltage when the input current is constant. So see here, this is very important. See here when the output, here when the input. Clear this area, this point is very important. It's very important. Input character, input with input, and when the output voltage. Output is output without when the input current is constant. See this now. We have here area. See my friend, current starts from, for example, this area, then increase. So what we have here? First of all, we found that, okay, it's not to keep spin. IE equal IC positive IB. Okay. So if there is no IE is 0. What about this one? It is 0 equal IC positive I. This formula for majority. So majority current now is, or IE majority equal 0. If you remember, we draw this one. We draw this big current. This is majority, IE majority, and this one is now 0. But don't forget, we have IE minority. The collector, we have IC or IC minority. So this is the current, IC or ICPO. YEI CPO. IC, it's current. So collector, sorry, it's collector current. B, that's mean common base. and O, that's mean saturation or minority. So ICBO here we have, but ICBO here in microampere. See here in milliampere. For that reason, ICBO, we can say it's nothing. This is when I equal 0. Clear this area? Clear this point? Clear this point? So ICBO is a collector current when the input current is 0, i.e. is 0. For that reason, we cannot say there is no current in collector. We have a small current. It's current based on minority. We found that in I collector we have IC majority plus IC minority. Majority is 0, so just we have IC minority. So I collector common base, or that means minority. Clear for this? Clear this for you? So this is the first current, very important current. Second current we can see here is this one. IE increase, IC increase, see this IE. IE increase, IC is increased. And see here 1, here almost 1, 2, it is 2. That means IC usually a little bit equal IE because IB is very small. Sometimes we're gonna use this one. See this one. Third thing, current increase in this area, see? So we can here divide this throughout to 3 regions. First region, this one. When the input or output voltage is very small. So this is called saturation region. Dolo, full. If, see here, voltage is constant, almost 0. And current increase is constant. Line, like a line, no change. I will explain saturation later. This area called active region or ohmic region. Last region here is this one, cut-off region, no current, 0. So here we have 3 regions. Not in as output we have cut-off region, that's mean when IE is 0, and we have active region, and we have saturation region. So if I ask you an example, for example, what is the name of this area? For example, you have this area. What is the name? Take, for example, this volt. It is, for example, for VCB, it's 18. What is the output current? It is 4. So IC equal 4 when IE equal 4, and VCB it is here 18. This point, where is it? In which area it is? In active area. If I ask you if IE is 0, what's the output? See here. If IE is 0, IE is 0. So this is the current here, this point. What is the value? It's almost 0. When IE, so IC equal almost here 0. When IE equals 0, and VCB it is 18. Any question about this? So we have 3 regions. Now we can see in transistor we have in that we have just forward bias or reverse bias. But in transistor we have 3 regions, and those regions are very important: active region, saturation region, and cut-off region. Cut-off, that means doesn't work. We'll talk about those in details third hour. Any question? Do you have any questions? Clear for you? Which one is the best, online or at class? What do you think? Clear, more clear? Okay, doesn't matter. Let's take a break now. It's when we have 1 minute. take a break for 12. They will start the third hour at 12. Okay, don't go away. The same link at 12 we have to start, inshallah, third hour. Take care for yourself. Bye bye. Yes, good morning everyone. How are you? To continue the last hour today. Okay, we found here that we have active, cutoff, and saturation region. So we have three regions in transistor: active, saturation, and cutoff. And we'll talk about this in details later. Now, here we have active, cutoff, and saturation. I want to, okay, just a minute. See this with me, excuse me. Now I'll talk about those region. First of all, this is our transistor P in P, emitter, phase, collector. Now we are talking about regions in transistor. Keep in your mind this model: diode, opposite diode, E, B, C, forward. This is reverse, and this is emitter junction, collector junction. Now, let's talk about three regions. Region, emitter junction, collector junction. Emitter junction, this one. Collector junction, this one. First region is cut off region. In cut-off region, if you remember, here we have a power and here you have a power. In emitter region, that's mean this is off. Off. Emitter region off, that's mean this one is open. No battery. So if this one is off, that means this one is off. And here transistor doesn't. So off, off. Second one is active region. In active region, see my hand, my friend. Here we have something called on. That's mean we have a battery. On here, that's mean I have, see my hand, V, B, E equal 0.7. But for output, we have off. Off here, that's mean reverse bias. Okay, what that mean off here, by the way? See, off means here, okay, I will write here, off. Okay, here. of is two things. See here. First of all, we have VCB is reverse. That's mean we are working in reverse bias. Or see my hand, VCB is forward but less than 0.7 volt. So either I have here, see this is negative, positive. This is positive, negative. This is first case, reverse. Second case, no. It is negative with negative, positive with positive. But this battery is less than 0.7 volt. If you remember this explanation for this one, I will draw the axis. See, first all reverse bias, so it's reverse bias here. This is I with V. Second one, this one, VCB less than 0.7, this is VT. So see my hand. Also, this is off. So how many off do we have, region? We have two off. And after that, this is on. Here will be on. So for off, we have two cases. First of all, reverse bias. Second one is forward bias, but less than VT. So if I want to work as active region in transistor, first of all, you have to work here on that's mean bigger than VT, bigger than or bigger than 0.7, and collector junction should be off. Off that's mean either VCB reverse bias or forward bias, but less than 0.7. Third case is active, is saturation. Saturation, that means emitter junction is on that's mean bigger, and second one is on. On here, that's mean active, sorry, VCB forward and bigger than 0.7. So see here, this is active. See here, it is saturation. So repeat. For transistor, we have three regions based on E and G, EG and CG. So if EG is off, that means transistor doesn't work from the beginning. Now for active region, if emitter junction is on, but collector junction is off. Off means here two things. First thing, reverse bias or forward bias, but less than 0.7. Every time, this is, put this in your eyes and repeat this video many times. See, this is here. This is off. This is on. So now you are working on active region. If I got to work in saturation, that's mean on that's mean we have 0.7 for input, and for output I need forward and bigger than 0.7. Here or repeat. Clear or repeat arkadaşlar. Try to bring this table on paper and keep with you. It's very important because we're going to use this one in chapter 4. Now for chapter 3 this is, but for chapter 4 this is your summarization. So try to keep this with you and try to keep screenshot for this one, because we're going to use this one in chapter 4 about DC analysis for transistor or DC bias for transistor. Repeat anything clear for you, everyone? Should I repeat anything? Okay. Return back to our book. This is here they explain this one here, but I explained based on table. So a table is easier than this one. Now, using characteristics to determine the resulting collector current FIE3 and DCB is 10. Where is 3.8? 3.8 up 3.8. This one. So it's input characteristics. Okay, this one. He gives to me what's the value 3 milliampere and VCB is 10. So first of all, start with IE. IE is 3. It's 3 milliampere. VCB is 10C. This is up. They made the value. So IC it is 3 milliampere, and we are working on active region. It's clear? How we can use a graph to determine for the values and where we are working based on the graph, which is the region. Now, let's finish our explanation today. And we have like this. We have for transistor some parameter or ratios. See, we have DC mode. That means we have also AC mode. It's for electronics 2. Now for DC mode, we have ratio. If you remember, we have current starting from here to collector, and a little bit go to here. And also we have minority. Okay, keep this one up here, this one. Minority current. So this is IE, IB, IC, and here you have ICO or IC. So the ratio between IC to IE called alpha. So alpha it is IC over IE. We know that means IC equal alpha IE positive ICB. How we can find this one? See here, IC equal alpha IE, and we know IC is IC majority positive IC minority, IC majority this one. It's alpha IE capital letter positive I collector common base minority. So this is another formula. IC it's alpha IE positive ICB4. Now for bias I explained, so I explained that table, so you can ignore this one because I explained now. Breakdown regions is important, but I will explain. See if you return back to this graph. See this? Here before, excuse me. See this area? For example, I have here volts. This is what? 40, for example, 40 volt, called the breakdown volt. If I increase current over than this one, that's mean current in transistor will increase rapidly. Current inside transistor will increase rapidly. After that, my transistor will, after After that, my transistor will turn and the negative. So you have to work before break down voltage, because after this voltage, my transistor will stop working and will. So you have a range from 0 to 40. You have to follow until 30. Then you have to stop because you have to work at least 10%, 10% before the breakdown. For example, here, 36 or 35 volt is a maximum volt. Keep this as a distance between last working point and BV to avoid damage of your transistor. It's called the breakpoint voltage. Okay. Now we have another model called common emitter configuration. Common emitter configuration. See here, common emitter configuration we have, or we connected emitter to the ground. So for that region has common emitter. We connected emitter to the ground. So we have common emitter. And C input come from IB, output from IC. See the arrows, direction of arrows. Okay, same thing for here. So this one is N, PN, this one is B, N, B. I want to draw the symbol of this one, see? Base emitter and hit of arrow is correct? No, it's opposite. Excuse me, this is wrong. We have to correct the mistake. So see this one? Okay, let's check NPN here. No, it's correct. Here opposite. So this one. PNB, so this is like this. This is first. Second thing, let's see the voltage. Here, see this VBB and VCC, both are positive. It's wrong. You said we need some positive, some negative. Oh, and this is negative. This is negative. I will make this for you. It's very important. Base emitter collector. So this is VBE. This is VCE. And we have another volt called VCB. So if I want to write Kirchhoff, it is VCB positive VBE equal VCE. That's mean VCB equal VCE minus VBE. Why I need this? This volt is explaining, it gives to me information about active or saturation. And this is hidden, as you see. There is no, here I have VCE, I have here VBE, VCE, VBE. Where is VCB? This is V, and take care, VCB. Why VCB? Return back to common base configuration. I will draw again here. This is common base. This is common base configuration. This is VBE. This is VCB. As I told you before, the important model to understand transistor is common base. But the common model that we are using in our life is common emitter. But if I want to determine which model, which reason is my transistor is working on, active or saturation, because it's okay cut off, it's okay off. You have to find VCB. Keep this in your mind. So if I ask you which region, you have to calculate VCB based on this one. Is it clear? Okay. Now let's continue. See the transistor, bit of arrow. And now let's find the direction of current. In, out, in. We have 2 in, 1 out, or 1 in, 2 out. Usually IE equal IC positive I. Okay, now let's go to the curve. Same thing here, curve, but see this one. IB here in microampere with VBE when VCE output voltage is constant. Second thing is, see this one, it is IC with VCE when the input IB is constant. Okay, see here, let's study 3 regions: cut off, active, and saturation. So again, we have 3 regions, but we have something here. To jump in common base, active region is 0, or sorry, cut off region is 0. Here, see, here, friends, we have not 0. We have value. I know it's very small. For example, here at this point, it is almost 0.04 milliampere, but it's not 0. So ICPO is 0. You can see here. We can see I C E common emitter O not equal 0, bigger than 0. Here 0.04 milliampere. Good number. So we can see that ICO in common emitter is bigger than ICPO in common base. Why? Let's now explain this, and this is very important question. Okay, this is this explanation. I explained this before, so same. Here the explanation why. I see it's alpha IE positive IC. You already know this before. Now, IE is IC positive IB. Take IC outside. So now IC equal alpha positive IB over 1 minus alpha. ICBO 1 minus alpha. Alpha usually it is 0.996 to 999 without unit. What that mean? If you remember, alpha is IC over IE. That's mean 0.996 of IE will arrive to collectors. Give a big number. 0.996 of IE will arrive to the collector. And I have just 0.004 will go to the base. So how many? We have 990 for collector, and we have 0.044 for base. Yeah, it's nothing. I know it's nothing. For example, we can write another thing. 99.6% for IC, and we have just 4% for IB. So for that reason, sometimes you can ignore IB. You can say IC equal IB. Maximum value is 1. That's when IC equal IB. This is okay. Not exactly practical theoretical, you can say that, but practical we have a little bit now. And I will give you this number in exam. So IC, it is alpha IB 1 minus alpha, ICBO 1 minus alpha. So in saturation, in active cut-off region, this is 0. Cut off. So what do we have? We have this one. This value has a name. ICEO. Okay. Now let's discuss this number. Alpha usually it is 0.996. So it is ICBO over 1 minus 996. You can use calculator together and find the value. Calculator. Okay. Okay. Here try to use calculator. Yeah. 1 over, I want to practice here this one. 1, okay, we'll clear all of these. 1 over 1 here minus cancel. Clear. 1 divided by 0.004. That's 250. That's mean ICEO equal 250 ICBO. It's big number. Yes, I know. Big number. It's I know. So ICO is bigger than ICEO. This is okay. It's my calculator. Now it's okay. It's here. 1 over 1 minus alpha 996. This is the number 250. That's when ICEO is bigger than ICBO with 250. For that reason, see, we have this value. See, this 250 has a name called beta. Beta is IC over IB. I explain now beta. And see, for that reason, you cannot see here 0. We have a value. It's very small, 0.004, but we have a value. That drives me to explain another factor. We studied alpha. It is IC over IE and IE. And alpha, it is value between 0.996 to 999. Maximum is 1. We have here beta. See, output current over input current here. What is the value here? It's 250. From 250 value to 4 or 500. Okay, what does that mean? See here. It says IB input current. This is output current. If I have a small current in microampere, multiply 250, I will get IC. Which that means you told us IB current is very small. Yeah. But here we use this very small. Let's return back. And return up. Okay, we have 10 minutes. Okay. See here. Here, input current is very small, microampere. Output current is milliampere. So we changed from micro to milli. 10 exponential minus 6 to 10 exponential minus 3. This is called amplifier. That means here double I C equal beta IB, or you can see here amplifier. Why is amplifier? We call this one because IB current from micro, IC from milli. For that reason, we can say our current increased 10,000 times. If I have, for example, here 1 micro, I will get here 1 milliampere. That means my current increased 1,000 times. This is called current amplifier. And sometimes we call beta is current factor. Current factor, because see IB with IB. So now we have two factors, or two very important factors. What are they? What are they? First one is alpha, second one is beta. Here, beta, here. You find beta? Yeah, here, beta. Beta is IC over IB. And I told you, IB is very small. Sometimes we can ignore. But because we are using this IB as input, so we have big output. This is, see, if I want to draw here, equal, see, 10 exponential minus 3, 10 exponential minus 6. So here we have 1000. For that reason, this is called current. And for that reason, we got to use common emitter as amplifier. And this is the common one. I want the transistor to increase the current, to amplify my current. How we can do this? By using very small input current and get normal current, you can say, for example. So IB is micro and IC in milli. So the difference between micro and milli gives to me amplifier in current. Clear for you or repeat? I know a little bit long, but try to read at home later. Any question about this? Now, last thing today, is there any relationship between alpha and beta? Yes, we have. Let's find this one relationship. Okay, here. It's the explanation of the working point. Okay, keep this. If I want to change between alpha and beta, we have this formula. See with me. Alpha is beta 1 positive beta. Denominator is bigger than numerator by 1. Beta is alpha 1 minus alpha. Here, try to version this way. Alpha is beta 1 positive beta. Beta is alpha 1 minus alpha. Alpha 0995 until 0991, and you can see sometimes each one. Beta from 250 to 400. In exam, I will give this and this to you. Any question about this? Okay. Now for that reason, ICU, as told before, equal beta ICU. Okay, now we have breakdown, same thing what we said before for common base. We have breakdown here. See this breakdown from an emitter. See this again. If you increase volts on some volt, example here, see, then we have a breakdown. It's called breakdown voltage. Exactly like what we said before for common base. Okay, what do we have else today? Let's check our book. Okay, this is explanation breakdown. I see they explained here for us as I explained before. We have common collector, this concept, because a little bit used, so we don't need exam. Common collector. Limit of operation. Yeah, if you want to use transistor in your operation, you shouldn't use this transistor more than some volt. And this is called VC maximum. In what? How we can calculate this one? It's VC with IC. You have to multiply, and VC maximum they will give you in data sheet for transfer. So if you multiply IC with VCE, you shouldn't increase over VC max or your transistor will damage. This is again something like this. See this one. Okay, that's for today. Here we have data sheet for transistor C. if you want to see this transistor, see this, we have here a point. And see this one, this type. Here we have half cycle and 0. So this is B, this is C, this is E. Return back. B, C, and this is E. We will study something like this about how to know transistor in lab next year, about how we can use transistor and how we can use transistor in our mind. How can determine which PNB or NBN. So we have the graphs. It's not important for us, but some graphs for transistor. Okay, this is an example of our concept. We don't need those. Last thing is BC max. After that, all of these are concept. We don't need an example. Here, if you want, in our book, we can determine which one is NBN and BNB. Here, we cannot use transistor or ohmmeter. See here, if you are using ohmmeter, you have to find something like this. This is here to here, so it's 0.7. Here to here also should be open. VBE, see here, VCB. This is forward. This is reverse. Forward, we have value, for example, 0.7 volt. For reverse, it's open. That's we read in ohmmeter, it is infinity. For big number. For that reason, you can know which one is NBN or NBNB. Next week, okay, those are concepts. See, this is also concept. So here we have summary about this one. Explanation. And we have formula. Next week, I will give you this lecture also. There is no physical lecture, but I will go outside. I have something. So next week lecture is cancelled. And if I give you lecture, I will give you as online. Tamam? So next week you shouldn't come to class because lecture will cancel. And we try to find, for example, during the class, I try to give you a lecture as online. Clear? Repeat. Next week there is no physical class at class, but I try to give this lecture. I will try just revision for this and try to solve these questions next week as online. Okay, repeat. Next week there is no physical class because I have something, but try to give this lecture as online. Okay. What do you think about lecture today? Is good for you? Did you understand our lecture today? Did you understand my lecture today? Which one is better, online or offline? What do you prefer? You have less than a minute. Okay, it depends on people. Yeah. Anyway, thanks for joining us. Keep safe. It's a special case. For that reason, I give my lecture as online.